Welcome students. Today let us go with the applications of Gauss law. See, in our last class we have studied about the Gauss law, which states that the total electrical flux in a closed surface is equal to Q enclosed divided by epsilon 0, or by statement we can say that the total electrical flux in a closed surface is equal to 1 by epsilon 0 times the charge enclosed. So using that we are going to get an expression for the electrical field at a point due to an infinitely long charged wire. How you can able to get this? So for that I am considering a long wire, infinite long wire. See, when I am considering this infinite long wire, this infinite long wire is said to have the positive charges inside. So I am considering one more diagram also. So in this long conductor, I am saying that the long conductor or infinite long conductor is having so many number of positive charges in it. Okay. If you are considering so many number of positive charges, I am taking a point P at a distance R from it. I am taking a point P at a distance R from the infinite long charged conductor. Our task is to calculate the electrical field E at this position. See, in order to calculate the electrical field at this position, first of all, we have to consider a linear charge density. Let the linear charge density be sigma. Let the linear charge density be, considered to be lambda. What do you mean by this lambda? Linear charge density, it is nothing but charge per unit length. It is nothing but charge per unit length. That is lambda equal to Q divided by L. For a given length L, the total charge available will be equal to lambda into L. That's all. So if you are considering the surface, when you are considering linear charge density, charge per unit length, it is measured in terms of an unit called to be coulomb meter. So let us take this as equation number 1. For an infinite length, we can't able to say the amount of charges, but for a given length, the amount of charge available is lambda into L, where lambda is called to be linear charge density, or we can say charge per unit length. Now how we can able to apply the Gauss law to this infinite long charged conductor? So in order to apply the Gauss law to this infinite long conductor, I have drawn that long conductor again. Consider a point P at a distance R from the center point O. Now, in order to calculate the electrical field by applying Gauss law, you consider two small charged elements in this long conductor. One at the bottom, I am considering that charge element as A1, and one at the top, and I am considering this charge element as A2. Let us consider this charge element A1 and A2, and we should be clear that from the center point O, these charge elements A and the charge element A1 and A2 are at equal distances. Now you calculate the electrical field at this point P due to this charge element A1. So when you are considering this charge element A1, then from P, if you are joining this charge element A1, then the electrical field available at this point due to this charge element, since this is a positive charge, the electrical field will be acting away from that of that charge, perpendicular to that of the wire. So that is, let us take it out as E1. Similarly, if you are considering the electrical field at this point due to this charge element, You just drop a line from here, from A2 to what? From A2 to P. Then the direction of the charge element will be here. Let us consider it as E2. So due to these two charge elements, if you are having E1 and E2, then the resultant electrical field at this point will be, you can get the vector sum by applying the superposition principle, and the resultant we are calling it out as E vector. See, symmetrically, you consider another point on the other side of this charged wire. Let us consider that point as Q. Now, the point Q and the point O are again separated by the same distance R. Similarly, like that of the previous one, you consider the two charge elements A1 and A2. See, from A2, if you are considering this electrical field at this point Q, it is acting in this direction. And if you are calculating the electrical field at this point Q due to A1, it will be acting in this direction away from that of the charge, and the resultant will be acting in the opposite side direction to that of what? Opposite side direction to that of the previous case. So, in order to consider the resultant electrical field due to the two charged elements which points radially away from the charged wire, we can say the magnitude of the electrical field is same at all points if you are drawing a circle with radius r. You do one thing, keep O as the center, R as the radius, then you just draw a circle. So when you are drawing a circle, keeping O as the center and R as the radius, and you consider any point on the circle, let us consider this point as R, and let us take this point as S. Then at all these points on the surface of the circle, the magnitude of the electrical field is same and the direction acting radially outwards for these two elements A1 and A2. If you are considering these two charged elements A1 and A2, the electrical field on the surface of this circle is considered to be of same magnitude. So from this property, we can say that, or we can infer that the charged wire possesses a cylindrical symmetry. What do you mean by that? Let us explain in the next part. Before that, I will be writing. See, from this concept, from this diagram, or from this concept that I have explained, what you infer? From this we infer that, okay, from this we infer that, from this we infer that the charged wire possesses a cylindrical symmetry. A cylindrical symmetry. What do you mean by this cylindrical symmetry? In order to apply the Gauss law, we are in need of what? In order to apply the Gauss law, we are in need of a Gaussian surface. And the Gaussian surface should be symmetrical to that of the charge that you are considering. Here you are considering what? Here you are considering a long, infinite long charged wire. So in order to apply the Gauss law, we have to consider the Gaussian surface. And the Gaussian surface is a cylindrical Gaussian surface, because the infinite long charged wire possesses cylindrical symmetry. So how you can able to apply this Gauss law? By considering this symmetrical or cylindrical symmetry. Just you draw the diagram again. So I am considering a charged wire. When I am considering the charged wire, that infinite long charged wire is having the positive charge plus. And already we have stated that the linear charge density. Already we have stated that linear charge density, that is lambda, is equal to Q by L or you can say Q is equal to lambda into L. Now, what I am going to do? So, my task is I have to get the electrical field at the point P at a distance R from the conductor. Now, around this, that is around this conductor, in order to apply the Gauss law, around this conductor, I have to do what? I have to apply a cylindrical symmetry. If I want to apply a cylindrical symmetry around it, I am drawing a cylinder enclosing this point P. So, at the same distance on the other side, I am considering the point, and around that chart, I am taking a cylindrical surface. So, I am considering a cylinder as a Gaussian surface around this charged wire, so that this Gauss law can be applied. In order to apply Gauss law, we are in need of a Gaussian surface, and the Gaussian surface should be symmetrical about that wire or about the charge enclosed. Here, the charge enclosed is an infinite long conductor, and the Gaussian surface is a cylindrical Gaussian surface. Now, how to calculate the electrical field at this point E? See, in order to calculate the electrical field at this point E, let us calculate the electrical flux in this Gaussian surface. So I am considering I have to consider electrical flux in the Gaussian surface. What is the electrical flux in the Gaussian surface? See, Gaussian surface is an imaginary closed surface. As we know, the electrical flux is given by the formula phi E is equal to closed integral of E vector dot dA vector, or I can write closed integral of modulus of E vector modulus of dA vector into cosine of that angle cos theta. See, if you are considering the closed integral of E vector dot dA vector, here this Gaussian surface can be divided into three areas. One is the curved surface, another one is the top closed surface, and another one is the bottom closed surface. This top closed surface is one of the end cap of the cylinder, top end cap of the cylinder, and this bottom is the bottom end cap of the cylinder, and the side, the cylindrical surface, this Gaussian surface is having a cylinder, so that we are calling it out as the curved surface. So I am writing, I have considered a Gaussian surface. So this Gaussian surface is in the form of cylinder, is in the form of what? Is in the form of a cylinder. And if you are considering the Gaussian surface in the form of a cylinder, let the length of the cylinder be L. Let the length of the Gaussian surface be L. Okay, length of the Gaussian surface be L. Let us consider it as capital L as it is in your book. So the length of the Gaussian surface is this one. So this value we are taking it as L. Now, how to calculate the flux for this Gaussian surface? So I am writing it here. The flux, I have written it like this, isn't it? Flux phi of E is equal to, what is this? Closed integral of E vector dot dA vector is equal to combination of three surfaces. One is the closed curved surface, one is the top surface, end cap, top end cap, another one is the bottom end cap. So this can be written as integral of E vector dot dA vector for curved surface, plus integral of E vector dot dA vector, and when you are considering the surface means either the bottom end cap or the top end cap. So first of all I am writing it as top end cap or top surface. plus the third one, integral of E vector dot dA vector, and this we are writing it for bottom surface. See, when you are considering the curved surface, the top surface, the bottom surface, you can able to get the value for the closed surface area. So I can write this as phi of E is equal to, see, this can be written as integral of, if you are considering the curved surface, this E vector dot dA vector can be written as E into dA into cos theta plus integral of, when you are considering the top surface, then also I can write E into dA into cos theta plus integral of, when you are taking or considering the bottom surface, then again we can write it out as E into dA into cos theta. See, what is the value of theta? In order to get that, I am taking a small, infinitesimally small area on the top surface, bottom surface, and on the curved surface. If I am taking a small area on the curved surface, then the normal drawn will be in this direction, n cap, and the direction of electrical field also in the same direction, E vector, perpendicular to the surface and acting away. So when you are considering an angle theta on the curved surface, angle theta is equal to 0. Similarly, if you are considering a small surface area on the top or on the bottom end cap, the direction of the electrical field is perpendicular, the direction of the electrical field is acting away, the electrical field is in this direction. If you are considering the perpendicular or the normal drawn for the surface, it is n cap. So the angle between the electrical field and the dA vector or the normal drawn, that angle theta is equal to 90 degree. Similarly, when you are considering the small surface at the bottom, the direction of electrical field will be away from that of the charge. The normal drawn will be in this direction. So the angle between the normal drawn n cap and the direction of the electrical field theta is taken to be 90 degree. So here the angle theta is 0. Here the angle theta is 90 degree. Here also the angle theta is 90 degree. You take that values and substitute in this equation, what you can able to get. So I can get the value of phi E is equal to closed integral of, in case of curved surface, integral of curved surface E into dA into, what is cos theta? Theta is 0, so cos 0 plus integral of, in the top surface or along the top surface, E into dA into, I can write it out as cos 90 plus integral of, when you are considering it as the bottom surface, then you can say E into dA into cos 90. See, as we know, cos 0 is 1. This cos 90 tends to be 0. Here also cos 90 tends to be 0. So what is the value of the flux then? Then you can consider or get the value of the flux as phi of E is equal, okay, you can say phi of E is equal to, here we can write integral of E into dA for the curved surface, plus, since cos 90 is equal to 0, the flux due to top surface and flux due to bottom surface are becoming 0, which is equal to integral of the curved surface, which is equal to E into dA. See, what is this dA. On integrating, what you will be able to get? You will be able to get E, because electrical field on the curved surface, since the curved surface is symmetrical, it is considered to be a constant. So E into, when dA is integrated, you will be able to get A. But what is A? A is surface area of the cylinder. A is the surface area of the cylinder. What is the surface area of the cylinder? Surface area of the cylinder is considered to be circumference into height. So 2 pi r into length. Length is considered to be L. Instead of height, we have considered the length as L, height as L. So the area can be replaced with this value 2 pi r into L. Take this and substitute. Therefore, the flux available phi E is equal to electrical field E into, what is area? Area is 2 pi into small r into capital L. Let us consider this as equation number 2. See, we have calculated the electrical flux by considering the formula. What formula? The formula for the electrical flux, which is being written as closed integral of E into ds into cos theta. That we have already studied. But we have to apply the Gauss law to get the electrical field. So we will write like this. We know that according to Gauss law, we know that according to the Gauss law, we can write flux available phi E is equal to ratio of the charge enclosed by epsilon naught or permittivity. See, let us consider this means the charge available for that length should be known. We have written it in equation 1. So we write from equation 1, Q equal to lambda into L, since linear charge density lambda is equal to Q divided by L. So for this length L, the amount of charges enclosed inside the Gaussian surface is Q, and that value of Q is equal to linear charge density multiplied with L. That is, charge per unit length multiplied with the length of the conductor will be giving you the total charge available. Therefore, I can state the flux available due to Gauss law phi E is equal to, what is charge enclosed? Charge enclosed is lambda into L from equation 1. So lambda into L divided by this permittivity epsilon 0. Let us take this as equation number 3. Now you equate equation 2 and equation 3. Because both the left hand sides are equal, you have to equate both the right hand sides. So equating, so we can write equating equations 2 and 3. Equations 2 and 3. We can say E into 2 pi r L is equal to lambda into capital L divided by epsilon 0. See, very well you can say here you can cancel L with this L. What is the value of the electrical field now? The value of electrical field E is equal to lambda divided by 2 pi r into epsilon 0, or we can write lambda divided by 2 pi epsilon 0 into r. So the net electrical field at the point P due to an infinite long conductor is given by, therefore the electrical field E at that point is given by lambda by 2 pi epsilon 0 into r. See, from this equation it is clear that electrical field E due to infinite long conductor or infinite long charged wire, infinite long charged wire is inversely proportional to the distance r. Inversely proportional to the distance r from the wire. That is E proportional to 1 by r. But when you are considering the electrical field in case of point charge, see, this is a note, but we can say in case of point charge, okay, in case of point charge, the electrical field is inversely proportional to square of the distance. But in case of a long charged wire, electrical field is inversely proportional to the distance, just r, but in point charge it is r square. Now let us consider some of the special cases. What are the special cases that I have to discuss here? Let us take it as number 1. What is the value of the electrical field if the surface charge density is greater than 0 or less than 0? That we have to say. See, when you are considering the direction, the electrical field is always acting perpendicular direction to the wire. See, when you are considering electrical field, it is a vector quantity. So we have to say the direction. So I can write like this: the direction of electrical field is always perpendicular to the wire. Whether it is acting away or whether it is acting towards depends upon the nature of the charge, whether the charge is positive or whether the charge is negative. So I am considering the special case if the value of lambda, linear charge density or charge per unit length lambda is greater than 0. If lambda is greater than 0 means, then we are saying that the charge is positive. We have to consider that the charge as positive. Charge is positive. If you are taking the charge as positive, then the electrical field vector E points perpendicular to the wire, and outwards and acting outwards. That was the concept. Okay, that is, if you are having the wire and if you are taking the charge as positive or lambda greater than 0, then the electrical field will act perpendicular to that of the wire and in the outward direction. That was the thing I have written it here. If lambda is greater than 0, we have to take that charge as positive. Then electrical field E points perpendicular to the wire and outwards. Similarly, let us consider the point number 2. What is this point number 2? I am taking it like this. If the linear charge density lambda is less than 0, if it is less than 0 means then charge available is considered to be negative. Then the charge is taken to be negative. If so, then I can write the electrical field E vector points perpendicular to the wire. Always it is pointing perpendicular to the wire, but in what direction? But it is acting inwards. How I can represent if I am taking the long wire like this, having the charge as negative. If I am taking the charge as negative, lambda is considered to be less than 0. If I am taking the point P here, the electrical field at that point, that is, the electrical field is first of all perpendicular to that of what? Perpendicular to that of this wire, but the direction is inwards. It is acting towards the wire. This is what we are calling it out as what? We are calling it out as the special cases. If you are considering the distance, here the distance should be taken as plus r, and here if you are taking, the distance should be taken as minus r. See, here we have another point also we can represent. What is the another note or another special point that I can say? See, here we have derived an expression. See, if the wire is of infinite length, okay, we have taken that if the wire is of infinite length, with some charges that is distributed uniformly, then the electrical field at this point P at a distance r is given by the formula E is equal to lambda divided by 2 pi epsilon 0 into r. See, we can say this equation is true, or this formula, okay, this formula hold goods or true, hold good, or we can say true only in case of infinite long conductor, only in case of infinite long conductor, and it cannot be applied to final conductors. See, what will happen in case of final conductors then? See, if the wire is are of finite length, we can't say this is approximately correct. We can't say that it is exactly correct, since the electrical field need not be radial at all points. See, if you are considering, but in case of a wire, in case of wire with finite length, in case of wire with the finite length, the electrical field need not be, okay, the electrical field need not be radial, See, so we can't able to apply this equation, but what we will do actually, however, in that case, for such a case, what we can do, for such a case, this equation is taken to be approximately true. For such a case, this equation is approximately true. Approximately, we are taking it as true. Approximately true. See how you can say that it is approximately true, or how you have to find the electrical field in case of the finite wire. See, in case of the finite wire, what we have to do is, we have to take like this. If you are taking the finite wire means of a definite length means, we have to consider the point at the center. We have to take the electrical field at the center. That point should be far away from both ends of the wire. From this end as well as from this end, this point should be far away. Then it is considered to be what? Then it is considered to be approximately true. See, for such a wire, since it is approximately true, for that, the electrical field should be, for that, the point or the electrical field should be, taken at the midpoint, should be considered or taken at the midpoint of the wire, and it is far away from the edges, far away from the point that you have considered at the mid position should be far away from the ends or from the edges. This we are calling it out as the electrical field at a point due to an infinite long conductor carrying a charge Q. See, let us